Hello guys, let's learn about carbocations, carbanions, and free radicals. In every chemical reaction, there is a hidden middle stage. It's like the interval in a movie, everything depends on it. These are called reaction intermediates. If the intermediate is stable, the reaction is fast. If it's unstable, the reaction fails. Today we'll master the big three. These are carbocations, carbanions, and free radicals. Let's dive in. Meet the carbocation. At first glance, it looks like a normal carbon atom, but there's a catch. This carbon has lost an electron, giving it a positive charge. If we count its valence electrons, it only has 6 instead of the stable 8. In chemistry terms, it's electron deficient. In human terms, this carbon is incredibly hungry and unstable because it's missing what it needs to be complete. Because it only has 3 bonds, the carbon changes its shape. It adopts a planar geometry, as flat like a pancake, using sp2 hybrid orbitals. Notice that purple area stretching above and below the carbon. That is the empty p orbital. It's like an empty seat at a dinner table, waiting for electrons to fill it. This emptiness is exactly why the carbocation is so reactive. Now, let's talk about survival. If you are hungry, who helps you? Someone who gives you food, right? In organic chemistry, we call these helpers +I, or inductive effect groups. These are electron-donating groups, like alkyl groups. They don't give away their electrons entirely, but they push some electron density toward that hungry positive carbon to help neutralize the charge. Not all carbocations are helped equally. Let's look at the ranking. Tertiary is the king. It is surrounded by 3 alkyl groups. That's 3 friends, all pushing electrons at once. This makes it the most stable. Secondary has 2 friends helping. It's okay, but not as stable as the king. Primary only has 1 friend helping. It's quite weak and very hungry. Finally, methyl has no friends at all, just hydrogens that can't push electrons. This is the most unstable of them all. So, remember the golden rule: more donors equals more stability. The official order you need to remember for your exams is tertiary is greater than secondary, which is greater than primary, which is greater than methyl. Now, let's look at the flip side, the carbanion. Unlike the carbocation, this carbon has an extra electron, giving it a negative charge. Instead of being hungry, this carbon is electron-rich. In fact, it's feeling completely overloaded and crowded. It has a full octet of 8 electrons, but that negative charge makes it very unstable. Here's the stability rule: if you are carrying a heavy weight and feeling overloaded, what do you need? You need someone to help take that weight away. In chemistry, we look for I groups, also known as electron withdrawing groups. These groups act like a vacuum, pulling that extra electron density away from the carbon and helping it relax. But here is the shocking twist: the stability order for carbanions is the exact opposite of what we saw with carbocations. Think about it: alkyl groups are pushers. If a carbon is already overloaded with electrons, having friends push more electrons toward it only makes things worse. It's like trying to give a suitcase to someone who is already struggling to carry 5 others. Because of this, the hierarchy is flipped. Methyl is the king here. It has no alkyl groups pushing extra weight onto it, making it the most stable. Primary has 1 pusher, so it's a bit less stable. Secondary has 2 pushers, making it even more crowded. Tertiary is the weakest. With 3 alkyl groups all forcing electrons toward it, the carbon becomes incredibly unstable. So, for your exams, remember the golden rule for carbanions: less pushing equals more stability. The order is: methyl is greater than primary, which is greater than secondary, which is greater than tertiary. Finally, let's meet the free radical. Think of this carbon as a lone wolf. It has exactly 7 electrons in its valence shell. It's not quite at a full octet of 8, but it's not positively or negatively charged either. It is neutral, yet it feels incomplete. Because it is still short by 1 electron, it behaves very much like our hungry carbocation. It's looking for a little bit of help to stabilize its situation. The stability rule here is simple. Who helps a lone wolf? Someone who shares, right? Just like with carbocations, the free radical wants electron-donating groups, those +I alkyl groups, to push a little bit of electron density its way. This helps spread out the burden of that lone, unpaired electron. Because the needs are so similar, the stability order is exactly the same as carbocations. Tertiary is the king. It has 3 alkyl groups helping to stabilize that lone electron. Secondary is next, with 2 helpers. Primary is weaker, with only 1 helper. Methyl is the most unstable, standing all alone with no one to lean on. So, for your exam, just remember that the hungry carbocation and the lone wolf free radical follow the same path. tertiary is greater than secondary, which is greater than primary, which is greater than methy. Wait, there's one more thing that is absolutely vital for GPAT aspirants. While the inductive effect is important, there is a more powerful force at play: resonance. Take a look at this comparison chart. It summarizes everything we've discussed, but with a critical addition. You'll notice that for all three intermediates, carbocations, carbanions, and free radicals, resonance is at the very top of the stability hierarchy. In chemistry, the golden rule is that resonance always beats the inductive effect. For example, a simple primary carbocation is usually very unstable. However, an allyl or benzyl carbocation is significantly more stable, even though they might look like primary carbons. You know why this happened? Because the charge isn't stuck on just one atom. Through resonance, that positive charge or extra electron is shared and delocalized across multiple atoms. Think of it like a heavy burden. It's much easier to carry when it's shared among a group than when one person carries it alone. So, when you're ranking stability in your exam, always check for resonance first. Whether it's a positive, negative, or neutral intermediate, if it can resonate, it's going to be much more stable than one relying only on inductive, pushing, or pulling. Keep this chart in mind. Resonance is the ultimate stabilizer. Why is a triphenyl-methyl carbocation so incredibly stable? Let's see why. In a triphenyl-methyl carbocation, the central carbon is attached to 3 benzene-phenyl rings. While a normal tertiary carbocation is stabilized by the inductive effect of 3 alkyl groups, the trityl cation has something much better. The positive charge on the central carbon is delocalized over all 3 phenyl rings. Through resonance, the burden of that positive charge is shared by a total of 10 different atoms. Let's test your knowledge with 2 essential practice questions on intermediate stability. Question 1. Carbocation stability. Your task is to arrange the following in decreasing order of stability. Option A, tertiary carbocation. Option B, primary carbocation. Option C, secondary carbocation. And option D, methyl carbocation. Think about the hungry carbon rule. The correct answer is A is greater than C, which is greater than B, which is greater than dy. Because of the +I inductive effect in hyperconjugation, the tertiary carbocation has 9 alpha hydrogens and 3 alkyl groups pushing electron density toward the positive charge, making it the most stable. The methyl carbocation has no such help, making it the least stable. Question 2. The carbanion twist. Which of the following is the most stable carbanion? Option A, tertiary carbanion. Option B, primary carbanion. Option C, methyl carbanion. Or option D, benzyl carbanion. The correct answer is D, the benzyl carbanion. While you might be tempted to pick the methyl carbanion based on the inductive effect alone, remember the golden rule: resonance always beats inductive effect. In the benzyl carbanion, that negative charge isn't just sitting on one carbon, it is shared throughout the entire benzene ring via resonance. This delocalization provides a level of stability that simple alkyl groups just can't match. Master these rankings, and you're one step closer to acing your chemistry exams. In question 3, which of the following is the least stable free radical? The correct answer is D, the vinyl radical. Don't be fooled by the double bond. In a vinyl radical, the lone electron sits on an sp2 hybridized carbon. Because sp2 carbons are more electronegative, they hold onto electrons tightly and hate being incomplete. While the allyl and triphenyl methyl radicals are stabilized by resonance, the vinyl radical is extremely unhappy and unstable. Question 4. The resonance factor. Arrange these carbocations shown image in order of decreasing stability. Yes, the order is 1 is greater than 3, which is greater than 2. Here's the breakdown. Aromatic resonance in the benzyl group is the most powerful stabilizer because the charge is shared across the entire ring. Aliphatic resonance in the allyl group is next. The secondary butyl carbocation comes last because it relies only on the weaker inductive effect in hyperconjugation. Remember, resonance always wins. Question 5. The trap question. Does the presence of a nitro group at the para position increase or decrease the stability of a benzyl carbocation? The answer is, it decreases stability significantly. Think back to our hungry carbon analogy. A carbocation is already starving for electrons. A nitro group is a greedy electron withdrawing group with powerful -M and -I effects. Instead of helping, it pulls electrons away from the positive center, making the carbon even hungrier and much more unstable. Keep these electronic effects in mind, and you'll be able to solve even the toughest stability puzzles. If you like this video, Don't forget to like, subscribe, and share with your friends. Thank you. See you in next video.